This is part 2 of lesson 2 of unit 4, applications of derivatives. We are going to look at a graph. So far we have looked at a table, we looked at an equation. We're now going to look at a graph, and then at the end of this video we're going to look at some calculator related questions for straight line motion. So example 3, the graph at right is y equals v of x. It's a velocity graph of an object moving on a line over the time interval 0 to 10. Assume that the positive direction is to the right. So some things we can see from this graph is from 0 to 4 on the time scale we have negative velocity, and then from 4 to 10 we have positive velocity, and we have 2 sections of constant velocity from 0 to 2 seconds and from 6 to 8. Okay, so now answering the questions. Part A says, on what interval of time is the object moving to the right? So that would be where it has positive velocity. So we're looking for where v of t is greater than 0. So that is anywhere greater than 4 seconds but less than 10 seconds, or whatever the time interval is. It's not specifically given, so I may say seconds just out of habit. Part B says when is the object speeding up? So we want the object speeding up when v of t is, not specifically greater than 0. When v of t and v prime of t have the same sign. So we want in 0 to 4 seconds, we want, so v of t is less than 0, so we would want v prime of t to also be less than 0. And you can see that we have a positive slope along this part of the velocity and a 0 slope here. So this does not occur. So we don't have a part of the graph between 0 and 4 seconds where the derivative of the velocity is negative, like the velocity itself. But what we do see is that on this section of the graph, from 4 to 6 seconds, the 4 to 6 time interval, we have velocity being greater than 0 and its derivative also being greater than 0, because we have a increasing line. And here we have 0 slope, and then we have negative slope. So the circled part from 0 to 4 seconds is the only part where we have an object speeding up. So we're going to put 4 is less than t, which is less than 6. Okay, next question says, how fast is the object moving at t equals 3 and at what direction? Okay, so how fast is its speed? So if we look at, let me erase all this. If we look at t equals 3, we are right here. And we have a v of 3 equal to -5. So the speed is going to be the absolute value of that, which is going to equal 5. And moving to the left, since the velocity is negative. All right, next question says, what is the average velocity over the time interval from 0 to 4 seconds and then 4 to 10? Show the computations that lead to your answer. So what we want to remember is on the first page, where we were given our review, is that it says the average velocity is displacement over the elapsed time, and that the displacement is, come on, let go. There we go. The displacement is, I think it's on here somewhere. Maybe not. Okay, it's not. But if you recall from when we did this before, the displacement is the area under the curve of a velocity graph. So what we're going to have to do is find the area under the curve and then divide it by the time interval. So that's what I'm going to write down what I'm going to do. I'm going to put, so how we find the answer, we are going to take the displacement, so the velocity average is going to equal the displacement divided by the time interval. And this displacement is the area under the curve. Okay, so we have two sections here we're doing this for. The first one is from 0 to 4 seconds. So the velocity average is going to be, so let's find the average under this curve, I mean the area under this curve. So we can divide it into two sections. We have a little rectangle here that's 2 by 10. So that's going to be 20, and it's going to be negative because the velocity is negative. And then we have a triangle that's half its size, so this area is negative 10. And then we have a time interval of 4. So that's what we're going to divide. So we are going to have negative, go away, negative 20 minus 10 over 4 seconds. So it gives us negative 30 over 4, which is negative 7.5. And then for 4 to 10, so we have, there's two ways you can do this. You could divide this up into two triangles and a rectangle like this. Here at 6, I thought I pressed that. Here at 6 and here again at 8. I'm just going to do the trapezoid. I have a base that is 6 units and a base that's 2 units, and I have a height of 15. It's the same difference, but however you see it is fine because you're looking for the area of that shape. So I'm going to have, and I'm going to put it over here. So my velocity average, I'm sorry if you don't have enough room on your paper, is going to be, and they're going to be positive. So I have 1/2 6 plus 2, those are my two bases. You average the bases and then multiply them by the height. And then I'm going to divide it by the time interval, which is 6 units. So I get 60 over 6, which is going to be 10. So those are my two average velocities. Okay, what is the total distance traveled by the object? Show the computations that lead to your answer. Well, we've already really done them. So what we're going to do is we're going to add up the two areas under the curve. So we're going to do the area from 0 to 4 plus the area from 4 to 10. So we have, and remember, this is going to be the absolute value because we want distance, not displacement. So we're going to have 30, because here's our computations, plus, so I'll be more accurate, I'll be like that. So plus 60 is going to be 90 units. Okay, part F, when is the object slowing down? Justify. So there's two places where the object is slowing down. It's when the velocity and the acceleration are going to have opposite sides. So that is going to occur in this section from 2 to 4, because I have positive acceleration and negative velocity. And it's also going to happen from 8 to 10, where I have the opposite is true. I have positive velocity and negative acceleration. So the first one is going to be from 2 to 4 seconds, because v of t is less than 0. and v prime of t is greater than 0. And from 4, oh, I'm sorry, it's not 4. It's from 8 to 10. I'm sorry, I don't know why my computer is slow to respond today. So v of t is greater than 0, and v prime of t is less than 0. They have opposite signs. When is velocity increasing? It's going to be where the velocity and acceleration have the same sign. And there's only one part on this graph where that happens, and that is this one section right here between the time unit of 4 and 6, because we have positive velocity and positive acceleration. We have a positive slope on that part of the curve, and we have positive velocity. We have no negative slope with a negative velocity. So that green section is the only section where that occurs. So we're going to write between 4 and 6. And why is that? Because they have the same sign. The velocity is greater than 0, and its derivative, the acceleration, is also greater than 0. And finally, on what intervals does the object move at constant speed? And I discussed that at the beginning. When you first analyze your graph, you should look at things like that, so it'll be easy to answer those questions quickly. And you can see there's 2 areas where we have 0 slopes. That's from 0 to 2 seconds, and then from 6 to 8 seconds. So we are going to say 0 to 2 seconds, and from 8 to 10 seconds. And though it doesn't ask us, what we want to say is that v prime of t is equal to 0. So that's how you read a velocity graph. Now you want to be careful when it's asking for things like the average acceleration. You want to remember that the displacement is the area under the curve, and that the distance is the absolute value of the displacement. So you've got to find the area under the curve. And you're going to find on these problems that they will give you shapes that you can find the areas of pretty simply. By the time we get to chapter 6, you're going to find that they can give you more complex curves where we have a different way of finding area under the curve, and that's going to be the integral or the antiderivatives. But we will get to that eventually. Okay, finally, I want to do this calculator question. I'm going to do 4, 5, and 6. I'm going to skip 7. I think it's a little redundant, so I don't feel a need to do that one as well. So we are going to need our graphing calculator for this. So I'm going to open that real quick. And I'm just going to use the 84 because it's the easiest one for me to grab here. If you have an Inspire and you want to know how to do this problem, and you're not sure how to do it on your own following the steps for the 84, please ask in class, and I will gladly go over that with you. Okay, example 4. An object moves along the x-axis for time 0 is less than or equal to t, less than or equal to 6. The velocity of the object at time t is given by the function v of t is equal to the natural log of t minus 0.15 t cubed plus t squared plus 2t to the 4/5 power. For t equal to 4, is the object speeding up or slowing down? So what we want to do is we want to, in our calculators, and I'm not going to show this part, we're going to put v of 4 in. So we're going to take the natural log of 4 minus 0.15 4 to the 3rd plus 4 squared plus 2 times 4, and that's going to be raised to the 4/5 power. A lot of 4's here. Okay, and that's going to be approximately equal to 4.497. So that's our velocity at t equals 4. Now we want to find the acceleration. Now just as a review, What I'm going to do is show you how to do this in your calculator. You can look at the graph, but you could also do it in this using our dy dt function. So a of 4, which is v prime of 4, is going to be approximately equal to, so what you want to do, there's the function. I mean, you could search for that. If you're looking on the graph where the particle's slowing down, that's going to be where the acceleration is 0. So that's going to be a horizontal tangent line, which you can see on the graph is about a little more than 4-ish. It's hard to see really, but that's why this little function is really nice. Our end deriv, if you have an Inspire, it's right in the list of, if you're on a calculator page and you press menu and you go under calculus, it's right in there, end deriv. So I'm just going to use x, and then I'm going to type my function in, which is ln of x minus 0.15 x to the third power plus x squared plus 2x, and that's raised to the 4/5 power. And then I want to evaluate that at 4. And I get negative 2.173. So this is equal to negative 2.713, which is less than 0. So it is, our particle is slowing down. Since v of 4 is greater than 0 and a of 4 is less than 0, opposite signs. At what time in 0 to 6 seconds does the particle change directions? Justify. So looking at our graph here, we want where v of t equals 0 if it has to change directions. So on the graph, you can see that we have 2 zeros. One's exactly at 6 seconds. Is that at 6 seconds? 1, 2, 3, 4, 5. Excuse me, 5 seconds. But we're going to look at the first one. So I'm going to do second, calculate. I'm going to find my 0 and my left bound. Let me put it right there. And my right bound right there. And I get a 0 at 0.391 seconds. The nice thing is on the, I guess I don't know it's seconds, is that on the Inspire, if you just hit graph trace, it'll stop at the zeros and it'll highlight that it is a 0. So there's a little less work for some of these options on the Inspire. So this is 0.391. V of t is changing from a negative value to a positive value. Okay, and so that's the one. And then we have to find the other one, which we said was right around 5 seconds, but let's do it just to verify. So we're looking for a 0. So let me move this all the way over here. So if you had your Inspire, you could just keep tracing along here. And, oh, there, I should have showed you that. Let's just keep on. So here's our other 0. And it is pretty darn close to 5. So 5.00, what was that number? 5.008. The particle changes from positive value to a negative value. Okay, next problem. Number 5. We're just going to do number 5 and 6, and I'm going to skip number 7. I didn't see any additional value of doing that one, so we're just not going to do it. Okay, number 5. A particle moves along the x-axis so that at any time t greater than or equal to 0, its velocity is given in meters per second. So now we do have units. V of t is equal to 4 plus 2.3 sine of 0.85 t. What is the acceleration of the particle at t equals 4? What does this tell you about the direction of the particle? Okay, so what we want is v prime of 4. Oh no, I'm looking at the wrong, sorry, I'm looking at the wrong part. I put that in the wrong part. So we're up here. So we're looking for v prime of 4. And so we're going to do what we did before. We are going to use our derivative calculator. So we are going to, at x is our variable, and we're going to put in our function, which in this case is 4 plus 2.3. I always put the times sign there because I'm never sure if I have to have it or not. And that way I don't have to worry about getting a false answer. And we're evaluating this, whoops, at x equals 4. And when we do that, we get negative 1.89. Okay, and we can see it's negative, so that means the acceleration is pushing to the left, so that's what we're going to write. So v prime of 4, which is equal to a of 4, is approximately equal to negative 1.890. The particle is being pushed to the left at a rate of negative 1.890 meters per second squared. It's going back from my physics days when I used to just write an S, but math books always seem to put sec squared. Okay, and then finally number 6. An object moves along a line so that at time t between 0 and pi, its position is given by s of t equals negative 3 times sine of 0.25 t squared plus 1. What is the velocity of the object when its acceleration is 0? Describe the behavior. Now you want to be real careful, and that's why I like these two examples. Number 5 is a velocity function. So if we're looking where it changes direction, we're looking where the derivative equals 0. Now, number 6, on the other hand, is a position function. So if we want to know when its acceleration is 0, that's those inflection points we have talked about, and we'll be talking about those again. So remember, it's the halfway point between where the concavity of the curve switches from negative or positive. So we're not going to have a 0 derivative. We have a 0-second derivative. So what we can do is we can look, and this is going to be an approximation, and you just want to make sure that you mention that in your description of your answer. So if we're asked to use a calculator, because it could be a function that the derivative is a little, ugly and time consuming to do, so you may not want to take the time to work it out. I mean, the chain rule might just be really horrific and not worth your time. So it might be okay if you explain your answer, and remember, it's in a calculator section for a reason, so don't try to kill yourself. So what I'm going to do is put the function in, And now I'm going to look at my graph, and you want to remember that pi is about, 3.14. So we're going to be looking in that range. You want to make sure you're looking in that range. If you notice that in the center section of the function, behavior is a little different than the rest. Okay, so we want to know in this time frame where the concavity is changing. So if you look at 0, and I wish I could mark this up, hopefully, yeah, you can see my pen mark, that here we're concave down, and then right along here somewhere we change to concave up. So we're looking in this area right here. So what we want to notice is right along here somewhere, about this center point, is where it changes concavity. So if on your paper you wanted to sketch a quick little graph like this, that you are looking for the inflection point. So if I were to do this, and I would have this graph like that, I could put here that I'm looking for the inflection point. And you can put a of t will equal 0. That will let the graders know that you understand what the question is answering and that your answer is an approximation. Okay, now looking at our graph again, and I don't know why it won't come. Okay, looking at the graph, I'm just going to graph trace, and I'm going to try to approximate when I feel like I'm about halfway along this curve. And as you can see, it's kind of in where the displacement is going to be negative. So I think that I'm going to go with that. I'm going to go with that point. Now yours might be a little different than mine, and if you want to find it exactly by taking the second derivative and setting it equal to 0, have at it. But that's a lot of time and effort. Okay, so I am going to put at that t is approximately equal to 1.515, and then I'm going to find v of t, v of 1.515, because we want to know what is the velocity. So this is approximately equal to negative 1.9086. Okay, and how did I get that? By going in my calculator and doing the end deriv again. Whoops, I did not want to do that. Whoops, I did not want to do that there. Let me get out of my graph and do it here, like I should. So x, and then I'm going to have negative 3, whoops, not tangent, negative 3 sine 0.25 x squared, and then plus 1. And we're doing this at our point, which is 1.515. And there's that value I got. Okay? Which they wouldn't expect to see the work for that. They would expect you to do that in your calculator. And since it's negative, we're going to say the object, because we're supposed to describe the behavior. The object is moving to the left. Okay, so that's how you would work the calculator questions. Again, as always, we'll be going over this in class tomorrow, and I'll answer any questions that you may have.